You're filling up your car at a gas station. You unscrew the cap. You smell something acrid. That's crude oil. Raw, unprocessed, straight from the ground. And here's what most people don't realize. You cannot burn that raw crude in your engine. You cannot pour it directly into your car. You cannot turn it into plastic or jet fuel or asphalt without transforming it completely. Raw crude is useless. And yet the entire modern world depends on it. So how does a sticky, disgusting, unusable liquid become the fuel in your car, the jet fuel in airplanes, the plastic in your phone, and the asphalt under your feet? The answer isn't obvious. It requires one of the most impressive industrial transformations humans have ever engineered. To understand how this works, we first have to go back to 1859. A man named Edwin Drake drills into the ground in Titusville, Pennsylvania. Black liquid shoots up. At the time, nobody really wanted crude oil. What people wanted was kerosene for their lamps. So, refiners heated crude in basic stills, pulled out the kerosene, and threw the rest away. They were wasting most of it. Then came the automobile boom. Henry Ford introduced the Model T. Suddenly, gasoline demand skyrocketed. Refiners couldn't throw away all that crude anymore. They needed to transform the entire system. They needed to be smarter. That's when refining technology evolved from a simple heating process into the complex engineering system we see today. Here's the thing. Crude oil isn't one substance. It's a mixture of hundreds of different hydrocarbons, molecules made of hydrogen and carbon. Some are light and evaporate easily. Others are heavy and thick. And this is where engineering gets really interesting. Inside a refinery, crude oil is heated to around 354 degrees Celsius. This turns most of it into vapor. That vapor then enters a tall structure called a distillation column. Imagine a tower over 30 meters high. Different hydrocarbons have different boiling points. Lighter molecules condense higher up. Heavier molecules condense lower down. As vapor rises inside the column and cools, the molecules separate. At the top, you get refinery gases like propane and butane. Below that, gasoline. Below that, kerosene for jet fuel. Below that, diesel. At the bottom, heavy gas oil and thick residue. In one step, crude oil is separated into different fractions. Each one is useful. Each one is valuable. But here's the problem nobody asks about. Crude oil naturally contains way too many heavy hydrocarbons. Modern society needs gasoline and lighter fuels. The distillation column alone cannot create enough. So refiners do something radical. They crack the heavy molecules. Cracking is exactly what it sounds like. Breaking large hydrocarbon molecules into smaller ones, using high temperatures and pressure. One of the most important processes is fluid catalytic cracking. Heavy gas oil is exposed to a fine catalyst powder at high temperature. The catalyst speeds up chemical reactions that split long hydrocarbon chains into shorter ones. Suddenly, refiners produce more gasoline and other valuable fuels. Without cracking, modern refineries simply wouldn't have enough gasoline to meet global demand. But this is where it gets even more interesting. Some fractions like naphtha aren't very useful on their own. They need to be chemically rearranged. That's where catalytic reforming comes in. Instead of breaking molecules apart, reforming reshapes them. Straight-chain hydrocarbons are converted into ring-shaped or branched molecules. Why does this matter? Because these structures burn more smoothly in engines. This process increases a fuel's octane rating, its resistance to knocking in engines. High-octane fuel allows modern engines to run efficiently and safely. Then crude oil naturally contains sulfur. When burned, sulfur forms sulfur dioxide, a major air pollutant that contributes to acid rain. So before fuels are shipped out, they must be cleaned. In hydro-treating units, hydrogen is used to react with sulfur compounds. The sulfur is converted into hydrogen sulfide gas and then removed. Modern environmental regulations require ultra-low sulfur fuels. Many countries now limit sulfur in diesel to just 10 to 15 parts per million. Even after all these processes, gasoline isn't finished. It's a carefully blended mixture of different components: cracked gasoline, reformed gasoline, alkylate, and additives. Refiners adjust blends depending on climate and regulations. Winter fuel formulas differ from summer ones to control evaporation rates. Diesel, jet fuel, and other products are also blended to meet precise specifications. Think of it like cooking. Distillation gives you ingredients. Cracking and reforming modify them. Blending creates the final recipe. Here's something almost nobody knows. The term cracking didn't come from a textbook. Early refineries discovered it by accident. Barrel stills would literally crack and split from the heat. But instead of seeing failure, engineers realized the cracked barrels were producing lighter, more valuable products. An accident became an innovation. A disaster became the foundation of modern refining. The next time you pull up to that gas pump, remember this: the crude inside that pump has been heated to extreme temperatures, broken apart into fragments, rearranged at the molecular level, cleaned of impurities, blended with precision, transformed dozens of times over. That's the hidden engineering behind the simplest moment of your day. Modern life runs on transformation, and it all started with learning how to break things apart and rebuild them better.